So yeah, I'm a researcher at UCL, and I'd like to share some of our research trying to monitor the brain health in babies in critical care. So a bit of background about me. I grew up in Shropshire, and I was quite interested in physics and maths. So I went to Imperial, where I studied physics, and there I picked up an interest in medical physics and using physics for medical applications in general. I did my master's at Cambridge in photonics, which basically means using optics. And I've done my PhD at UCL, where I still am, and I'm going to share some of my work from my PhD, but also now as a researcher. So this video sort of shows you the measurement that I'm trying to achieve. So if we zoom into the baby's head and we zoom into the neurons, we get to the mitochondria. So the mitochondria is where metabolism happens, which is where oxygen and glucose are converted into energy. And you might be able to see that when this process happens, there's a color change that comes from the membranes in the mitochondria. And if we zoom in here, we'll see that the color change is from one of the enzymes, the very final enzyme actually that passes electrons to oxygen, and that changes color every time that happens. So that's a really interesting phenomenon, because if there's a color change going on inside neurons, can we measure that? And can we have an optical measure of metabolism? So that's what my work is focused on. So the reason that we can measure that is because infrared light is quite transmissive through tissue. So I'm sure that you've all shone a torch through your fingers. I think I can do that with the laser pointer, not very brightly. But if you shine a white light through the hand, you'll transmit red light out the other side. And that's because the red end of the spectrum transmits quite well through tissue. And if you look at this picture here, I hope you can see that the red light is coming well through the hand. And the thing to notice here is that there's no shadow from the bones. So that's telling us that the red light and the infrared light, which is a bit further past the visible spectrum, actually transmits really well through bone. So now we know we can interrogate through bone using infrared light. What we want to do is use it to not just look at hands, but they do that with pulse oximeters in hospitals every day. We want to look at the brain, and with babies' brains, their skull is quite thin, so we're able to inject or just literally shine infrared light into the head. The light will diffuse as it does through the hand, but some of that light will travel through the head and will be able to be detected a few centimeters away. So the light that we detect will contain information about the colors that are within the brain. And as I just showed you, those colors can be related to physiological processes such as metabolism. So NearInfrared Spectroscopy, which is the technique that we use to do this, has traditionally and for the last 30 years been monitoring changes in oxy and deoxyhemoglobin, so blood oxygen levels. And I'm sure most of you will know that blood, depending on how oxygenated it is, will change color. So arterial blood, so blood that's really heavily oxygenated, will be really bright red, whereas blood from the venous, the deoxygenated blood, will be more dark purple. So just by looking at the blood, we're able to assess its oxygenation. So people have been doing this for many years. What I'm more interested in, and my group at UCL, we're looking at this enzyme at the end of metabolism, because that really gives us an insight into how well the cells are using oxygen. Not just whether oxygen is getting to the cells, but whether the cells are still alive and working. And we believe that there's much more clinical relevance of measuring metabolism. So, as I said, oxy and deoxyhemoglobin have these different spectra, so that's the different colors. Cytochrome C oxidase, which is our metabolic signal, also has a spectra, and it's shaped like this in the infrared. So how we measure this, how we interrogate the brain, is we use broadband light, so we shine a white light source, and it really is just a halogen bulb, shine that into the head, and then we detect what comes back out. And using some really simple physics, we're able to separate the spectrum that we get back out of the head. Using the knowledge of what the colors should be, we can calculate the concentration changes. So just by detecting attenuated light from the head, we're able to tell doctors that metabolism and oxygenation is changing. So this is an example of the spectrum that came from a baby in its first day of life. And you can just about see that there's two spectra here, and there's a shift in the peak. And that shift is due to the level of oxygenation that baby was experiencing. So this is the system that I built. So this was my PhD, which was building a system that was able to do this, but within the intensive care unit. Very briefly, we have a bulb. We illuminate optical fibers, which are held onto the head using a very simple probe holder. And then a bit further away, there are some detector fibers which take it to a spectrometer, and that's how we get that spectrum. And then on a laptop, we can, in real time, calculate the changes in oxygenation and metabolism. So this is what Cyril, my machine, looks like. It's in very rough academic form. We're a long way from a spin-off company, but you can see there's a light source down here. There's optical fibers which go into the baby's cot, and the optical fibers that come back out to the spectrometer, and we display in real time the concentration changes on the laptop. And you can see that the neonatal intensive care unit, so looking at really sick newborn babies, is a very busy clinical environment. There's lots of other monitors, so we have EEG, heart rate, lots of different things. So it's been the biggest engineering challenge, I would say, is getting a system that works with the clinical team minimally invasively. So what population are we studying with this metabolism monitor? We're studying hypoxic-ischemic encephalopathy, which is a fancy word for baby brain injury. So these are babies that have a healthy pregnancy, but there'll be some sort of trauma or difficulty around the time of birth, leading to a restriction of blood and oxygen to the brain. It's not very common. It happens in 1 or 2 babies per 1,000, but it's the leading cause of cerebral palsy in infants, and it's also one of the leading causes of death in infants. So it's a very serious and devastating disease. Currently in the neonatal intensive care unit, babies are monitored from as soon as they're born with EEG, so we're monitored the electrical activity. But the gold standard, the best way to assess the injury, is using an MRI scan. And you can see here that the MRI scan is able to tell you, based on the metabolism in the brain, whether you've got a normal brain or a very injured brain. The problem with this is that the MRI is obviously not in the intensive care unit, and babies will need to be transferred, and you only get a single time point. So these babies, even though they're really in need of this MRI, aren't able to get there until potentially up to the end of their first week of life. So they have a full week of life where the doctors don't really have any information about the level of their brain injury, and they're having to treat them basically as a black box. So that's where we think NearInfrared Spectroscopy could come in, because we're able to provide a continuous measurement of metabolism at the cot side without too much interruption to the daily clinical care. So this is another picture of our system in the hospital on a baby. So this baby had hypoxic-ischemic encephalopathy, and we monitored this baby from the very first day of life, as soon as we could get access to the parents and approach them for consent, because this is still an observational study. And we monitored this baby from its first day of life up until the end of its first week of life, when it has the MRI scan. You can see here that the black probe holder on the baby's head, and that's just held on with sticky tape, and it really doesn't interfere with the nurses and the doctors' clinical duties. We've had this system in the hospital at UCLH down on Gower Street. We've had it there since October 2013, and so far we've monitored over 80 babies with hypoxic-ischemic injury. So now I'm going to show you a couple of quite short examples of our data and why we think that we're really measuring something important and something that could really impact clinical care. So these are 2 examples of arterial oxygen desaturations in 2 different babies, so baby 7 and baby 21 from our study. This is a pulse oximeter reading of the oxygen saturation of the body. So this measurement would be done on the finger or foot. And you can see that both babies go through a period of normal oxygenation and then it drops quite rapidly. So here is a 20% drop. Here we have an even larger drop down to 70% saturation. And these are really severe events. If this happened to any of you now, we'd definitely be unconscious. So what we're interested in is if these babies are having these big saturation changes, just, in normal care, while they're in intensive care, how is this affecting the brain? And also, is the way that the brain responds to this, is that going to be able to tell us something about brain injury? So this is the brain signal, so the near-infrared spectroscopy signals we're getting during these desaturation periods. So you can see if you look at the red line, that's our oxyhemoglobin. It decreases at the same time as the arterial saturation decreases, which you would expect. And that happens in both babies. You both get a decrease in oxyhemoglobin, and you get a corresponding increase in deoxyhemoglobin, which is expected. What's really different about these two babies is that the cytochrome signal, so the metabolic signal, for the baby 21, it stays relatively stable throughout this really large oxygenation event. For baby 7, however, you see a really big drop. So you're seeing a huge decrease in metabolism because of this drop in oxygenation. And what we found after we did the MRI scan up to 3 or 4 days later, that this baby had a really severe injury, so a really poor predicted outcome, whereas this baby had a more mild outcome. So we were able to identify differences in the way metabolism responds based on the level of brain injury using our near-infrared spectroscopy technique. So what we showed in this study, and this was just a couple of examples of data, we did this on many more babies with a lot more statistical analysis, that we can measure metabolic response in the brain using NIRS, and also that we can identify the level of brain injury. And all of these, all the data in this study was taken on the first 4 days of life, so much earlier than the MRI scan can happen, and we saw a very strong correlation with our data and the MRI data. So that's a really promising avenue that we're following. On a slightly different note, some of the more exciting data that we've been getting is monitoring metabolism during seizures. A lot of the babies who have had hypoxic ischemic encephalopathy will experience seizures. And I'm going to present data from a case study where a baby experienced 5 recurrent seizures while we were monitoring with our near-infrared spectroscopy. So this is the first time that metabolism has been monitored in real time during seizure. So these graphs at the top show 5 seizures, 1, 2, 3, 4, 5. And the red period is, and this is the EEG, the amplitude integrated EEG trace, and this was used by our neonatologists to identify periods of seizure. So the periods of seizure are highlighted in red. Some of them are more easy to spot, so for example this one here. But EEG is quite a complex signal to interpret, and a lot of times seizures can go unnoticed. So if I show you the cytochrome C oxidase signal that we monitored at the same time, what you'll see is it's really, really strongly correlated with the EEG signal, that we get the same peaks at exactly the same time. And we looked at the temporal correlations to see that metabolism really is very strongly linked to the electrical activity. So we were seeing huge peaks in metabolism during the seizure period. Conversely, the oxy and deoxyhemoglobin signals, so our blood oxygenation, they weren't temporally correlated. In fact, we saw changes preceding the seizure, which was really interesting, and we're looking at more into that with more babies. The other thing that we also noticed is, this is showing all 5 seizures in a row, that the green is the cytochrome C oxidase signal. You see a decrease in the baseline, and we postulate that this is a monitor of injury caused by the seizure. So perhaps our signal could be a way of monitoring the level of brain injury that's induced by seizure. So this is quite exciting for us, and we're okay, perfect. This is the first time we've been able to monitor metabolism, and the fact that we can see such clear changes with cytochrome may mean that we could use near-infrared spectroscopy as a seizure marker, and further that we might be able to use it to understand the level of injury caused by seizures, which is an active topic of debate at the moment. So that's a quick snapshot of some of my research. I wanted to have a quick look to the future of, or my future and the future of near-infrared spectroscopy. And I recently watched 2001: A Space Odyssey for the first time. And despite all the amazing special effects, what really drawn my attention was that when they were monitoring in the sick bay, they had this monitor next to them, and it had this metabolic levels continuous trace. And I thought it was amazing that 50 years later, we still don't have this continuous metabolic levels trace, and that's what I would really like to provide, hopefully one day. I just want to give a quick shout out to Metabolite. So we've recently started a new public engagement platform. So we're working to try and share our research. So you can have a quick look at our website, and hopefully we'll be at lots more science festivals soon. And just acknowledge the team. We're a big bunch of engineers, physicists, mathematicians, and also the clinical team, the doctors and nurses that we work with. So thank you very much, and I'm happy to take questions.